Hello, my name is Hosman, and this is my optimization project for Dr. Jakiela's optimization course. As a brief overview of what my project is about, I'm attempting to optimize the blade design of a horizontal axis wind turbine by optimizing the angle of twist and core of the blade. Both of these vary as a function of wind speed and location, and traditional methods can be quite labor intensive, so I'm hoping to improve that by using a constrained multivariable optimization technique. So as you can see in these figures, the chord length is the width of the blade at any given location, while the angle of twist is how much it twists down the length. They both assist in the performance of the blade by reducing drag and increasing lift. To solve for these parameters, you have to combine both momentum theory and blade theory. Momentum theory looks at the wind before and after it passes by the wind turbine to determine how much energy is actually given to the blades, while blade theory studies how that wind is turned into thrust and lift and combined to create power. By combining both these analyses in both these methods, you result in getting these equations for which you can use to solve for the total induction factor B, the chord length, and theta P. As you can see by these boxes, they are actually quite dependent on U and R, your location and wind speed. So you can solve for an optimal chord length and theta P for any given speed in any given location, but then you have hundreds of different optimal designs which then have to be compared using this DCP value to determine which will give you the best power. DCP is actually your turbine power coefficient, which is proportional to your dP, or your power, and that can be solved for by using your total induction factor, which results from a C and theta P value. So by making this comparison, you can solve for your optimal design. But it's quite labor intensive. But if we were to take one step back and actually look at the equations to solve for your change in power, you'll see that there are a few things that keep popping up, that keep showing up. And you can see that your chord and your theta P, or your angle of pitch, are shown as shown here, are actually in your equations. And that can be used to our benefit because we're really just trying to maximize this dP value. If we allow the chord and the theta P to vary within a given range with the hopes of maximizing this equation, we should result in the same optimal design that we got from our traditional method, but with less math. So to start this analysis, I had to make a few assumptions as shown here, and these assumptions are then fed into both methods. So first up is the traditional method, where I used a lot of for loops to determine these optimal parameters and then compared them. And then I made an optimization method where I defined the function, the power function, and ran that through FMINCON for every section of the blade down the length of the blade. After running this analysis, it results in these two graphs, one being for the chord length and the other being for the angle of twist. So the chord length is actually quite accurate, and they match up pretty nicely. But if you look at the theta P, you'll notice that they don't quite match up, especially in the center. Though they vary about 30 degrees and they range about the same, this discrepancy is likely due to how the thetas are calculated. So in your traditional method, or any method, you have to assume either your theta P or your angle of attack. In the book method, you assume a constant angle of attack, but in our FMINCON analysis or optimization analysis, since you're assuming a theta P, you solve for this angle of attack in tandem and in real time, which likely led to this discrepancy in the graphs. But it doesn't mean one is less accurate than the other. It just means that your analysis needs to be improved, and these equations likely need to be accounted for. So in future goals, what I would like to do is find a better way of making this angle of attack consistent amongst the analysis so we can compare them better. And I would like to give a thank you note to Dr. Peters and list my references. Thank you for your time.